29 and 42 are now appearing. We saw that if we're solving this kind of question, and we have numbers which are small and large, like 4 and 105, that can be fast because of the small number. But here, now both numbers are large, and it's not clear whether there's some good way to solve this. I also want to emphasize, my 42 here is not even prime. That's not a huge problem, though, because the 29 and 42 are relatively prime. And so I know for sure that there is going to be some x that makes this work. The only question is which x. As we know now, one way to do this is to just find all multiples of 29 and hope that one of them works. Let me keep track of how much work is involved here. I have two options. I could look at 29 times 0, 29 times 1, all the way to 29 times 41. I could check all of those. That is 42 things to check. The other approach I could use is I could try multiples of 42. Of course, I'm not really doing multiples. I'll have to either add 1 or subtract 1 in either way. But if I take 42, I roughly have to check 42 times 1 all the way to 42 times 28. Here, there are 29 to check. The thing I'm trying to emphasize about this 42 and this 29 is that both of these are the original numbers. Both of these are as large as the original numbers. Why am I emphasizing this? I'm emphasizing this because if it wasn't just 42 and 29, but if instead the numbers were something like 29999x congruent to 1 mod 42325, hopefully these are actually relatively prime, I didn't check. But if this was the problem, then how much would you have to check? It would be so large that you would probably not want to do the question, because this is 30,000 things and this is 40,000 things. It turns out there is a very fast way to do this question, which can even do the second one. Now we need to think, what kind of ways could possibly make this faster? Here we're going to bring in a concept which we started talking about in an earlier lesson, but maybe which you never expected would be related to solving these equations. I also was saying that when I look at these kinds of questions, there's some symmetry between the 29 and the 42. Maybe I can use both at the same time. Also, I emphasized how important it was that the two had no common factors. It was very, very important for all of this that the greatest common divisor of 29 and 42 was 1. That is extremely important because otherwise the inverse might not exist. GCD, greatest common factor, greatest common divisor, is symmetric between the two numbers. GCD 2942 is equal to GCD of 4229. So GCD has this symmetry that we like. Well, how do I calculate the GCD? Let's just calculate that GCD for fun. But I'm going to say it's not exactly for fun, because there's something inside this equation we're solving for which the fact that the equation has a solution, that this equation 29x congruent to 1 mod 42 has a solution, this fact is somehow related to another fact, which is that the GCD of 29 and 42 is equal to 1. These two have some connection to each other. Well, then let's calculate the GCD of 29 and 42. Well, we know already that can't be too hard. I can just prime factorize the 29 and prime factorize the 42. Prime factorizing, 29 is prime, I'm done. That's hard to turn into something to do with this equation, though. So instead, I want to look at something slightly different, which is the other way of calculating the greatest common divisor. It's called the Euclidean algorithm. Okay, so what we had here is we were talking about the GCD between 29 and 42. I'm now putting them in rows. This row says that GCD of 29, 42 is the same as the GCD of 29, and what I do is I take 42 minus 29. It's always the gap. So I will be putting 42 minus 29, which is, if I can subtract here, I think it's 13. Okay, it's 13. Very good. If I have 29 and 13, the next thing I do is I keep this smaller one here, and I take the bigger one, and I subtract away, I take away the gap. 29 minus 13, that will give me 16. But I'm actually going to do that in two steps. I'm going to say I got 16, but I would still subtract the gap down to get 3. Here I've skipped a step of the Euclidean algorithm. In the Euclidean algorithm, I would first go to 16, 13, and then to 3, 13. But I'm already showing you that what really matters is I just subtract 2 of the 13s. Okay, well, now that I think about it this way, I have here this 3. If I have this 3, I'm going to subtract away many of the 13. I'm going to take the 3, and from the 13, I will subtract many 3s. I will go to 10, and then I will go to 7, and then to 4, and then finally to 1. Okay? And at that point, I will have found out that the GCD of 29 and 42 is equal to the GCD of 3 and 1. And I could finish here by already saying that that's 1. I could also finish by subtracting 2 of the 3s and getting to GCD 1, 1. But I'm already going to stop here. When you're doing GCD, if you see a 1 at all at the end, as soon as you get to one of them being a 1, the GCD is 1. Because the GCD of anything, 1, as long as the other thing is not 0, actually it's also, but anything, 1 is 1. I left space underneath. The reason I left space underneath is I want to write some things. I want to call 29 A, and I want to call 42 B. Let's look closely what happened. Here's my A, it's still 29. This 13, I'm not going to call it 13 anymore. 13 is B minus A. Okay. My 13 is still here. This 13 is still B minus A. What is this 16? This 16 is A minus, because I subtracted off a 13. It's minus 13. But my 13 is parentheses B minus A. Okay, I could do this. And this 3 here, this 3 is what happens when from the A, I minus 2 of the B minus A. Okay. This is messy. A minus 2 B minus A. I prefer to collect the A's and B's together. So let's rewrite this 3 as How many A's do I have? I have 3 A's minus 2 B's. You know, let's just double check a bit and make sure that we're doing the right thing. I mean, make sure that our math is right. We somehow are saying that 3 is 3A minus 2B. Is it? Let's quickly check. 3A. What's 3A? 3 times 29. That's 87. And what's 2B? 2B is 2 times 42 is 84. It's correct. 3A minus 2B is 3. So this works. This thing here, when I subtract them, I do get 3. Okay? Now, let me keep going. I now know that this 3 is 3A minus 2B. If that 3 is 3A minus 2B, now, if that was B minus A, if that was my 13, how many times do I subtract the 3? This 1 here that I end up with is B minus A minus a number of copies of 3A minus 2B. How many of the copies? Well, let's count. Minus 1 copy, 2 copies, 3 copies, 4 copies. So I need to minus 4 of those. This is minus 4 of 3A minus 2B. Okay. Now let's collect the B's and the A's in this very last expression. How many A's do I have? It looks like I have minus 1A here, minus another 12 A's there. So I have minus 13 A's altogether. Okay. How many B's do I have here? I have 1 B here, plus 8 B's there. I have 9 B's. So it looks like it is 9B minus 13A is 1. Is that really true? Let's double check. So let me just remember by putting onto the next screen, I find out that apparently 9B minus 13A equals 1, where A equals 29 and B equals 42. Really? Let's see. So I need to do 9 times B. That's 42 times 9. 2 times 9, 18. 9 times 4, 36. 37. Okay? I also need to do 13 times A. 29 times 13. 3, 9, 27. 3 times 2, 6, 87. 29 sits here. 7, 8, 9, 17. Carry a 1. 377. So we did not make a mistake. This is true. Why do we care? This seems like I just did the GCD algorithm, which you already knew the answer is 1. We did a lot of extra work to just get it 1. And furthermore, I kept dragging along. I kept all of these A's and B's. Well, there's a reason. Look, I have just proven that 9 times B, I've just proven that 9 times 42 minus 13 times 29 equals 1. What was my original question? My original question was, I needed to know 29 times what was congruent to 1 modulo 42. Something interesting is staring at me right now. What if x was minus 13? Well, what that means is that if x is minus 13, according to my equation up higher up, according to this equation here, 29 times minus 13, well, that's equal to, let me pull this across with a minus sign, minus 9 times 42 plus 1. What that means is that, yes, 29 times minus 13 is 1 modulo 42. it means that x is minus 13. Of course, that's a residue class. What that means is that the answer is either minus 13, or if you don't like minus 13, it's what is it modulo 42. So I can fix it by taking 42 minus 13. 42 minus 13 is pulling into 29. Really? That's quite a coincidence. That was actually unintentional. But we should just double check at the end that this actually worked, just to make sure that this method, which may be new to you, make sure that this method is okay. I'm claiming that 29 times 29 was the answer. Let's try. 29 times 29. 9, 9, 81. 9, 2, 18 plus 8, 26. 2, 61. Put down this thing. This is 58. 1, 4, 6, 8, 14, 8. 841. Okay? 841. We claim that 841 is going to be 1 mod 42. Actually, I can already see that, because 841 is equal to 1 plus 840. And 840 is very clearly a multiple of 42. 42 times 20. So this method works. How fast is this method? To compare how fast this method is, let's look back and see what is involved in doing it. The only thing I do is the Euclidean algorithm. I start with two numbers, however crazy they are, just two numbers. From those two numbers, I just keep subtracting the smaller one, and every time you subtract the smaller one, you just keep track of what they are in terms of the a and the b. And at the very, very end of the whole thing, you find that the number of b's and number of a's that you have are exactly the multiplicative inverses, actually, of both numbers. I'll mention that again in a moment. But I want to talk now about how much work is involved here. To do the Euclidean algorithm is very fast. Even if the two numbers are very big, as you subtract them, they quickly fall below each other and drop by half, and so on. This is what we call an exponentially fast algorithm, because it causes the numbers to shrink down very quickly. Very different from the way that you usually do this if you're just trying all multiples of 29 and all multiples of 42. Because if you do this way, you have what is called a linear time algorithm. You need to do every single one of these, or every single one of those. And if these are huge, it will take you a huge amount of time. But even these two numbers, even though they look big, if you use the Euclidean algorithm on them, they fall down very, very quickly. And this is actually a problem which you can do without that much time. The last thing I wanted to say is how this thing gave me both multiplicative inverses at the same time. You see, I found out this nice equation. 9 times 42 minus 13 times 29 equals 1. So what that tells me is that the multiplicative inverse of 29 modulo 42 is minus 13. The same equation tells me something else too. The same equation also tells me that if I'm trying to solve the equation 42 times y congruent to 1 mod 29, well, the answer is also staring right at me in the face, because 42 times 9, right there, 42 times 9 differs from 1 by a multiple of 29. So that's the symmetry I was emphasizing. Because the two problems of either going with the 29 or the 42 were somehow, because they were both interchangeable, it turns out that one method, based on the Euclidean algorithm, finishes them both at the same time. And this is one of the fastest ways to calculate the multiplicative inverse of any number. It's a trick, but it's a very powerful trick. And if you don't know how to do this, the question can take an extremely long time to finish.